Welcome back to the classroom. My name is Mr. Wong. Today we'll be covering Module 8 from the universe to the atom. Inquiry question 4, properties of the nucleus, and we're going to be looking at two specific dot points here. Now with the way this is going to go, we might end up splitting this into two videos. One talking about nuclear half-life, and then the second one talking about the process of nuclear fusion, and how we generate energy from nuclear fusion. Alright, for your textbook references, we have these two ranges here. We are looking at nuclear half-life, looking to model it, and then we're also going to look at nuclear fusion as well. Just to start ourselves off, in this particular dot point, we are trying to model firstly what half-life is, of radioactive decay, and then we are going to make some quantitative predictions, so numerical predictions about the activity or the amount of radioactive sample using these two equations here. The first and foremost important thing is to explain what a nuclear half-life is. Okay, and a nuclear half-life is when a radioisotope takes, or the time taken for the radioisotope for half of its radioactive sample to decay. Okay, you cannot change the half-life of any radioisotope through chemical reactions, through heating, and so on. This is purely within the nucleus of the atom, so any changes to the actual process of decay would be due to some kind of nuclear reaction. Now we can express half-life using the following equation here. This little n here represents the number of half-lives that have passed. And then you have nt and n0. So nt here is the quantity or the amount after the number of half-lives, whilst n0 is the original quantity. Okay, let's try and model half-life here. You can see that if we look at the time taken, every step of the way we are reducing half the amount of the radioactive isotope. What essentially means is it's the time taken for a radioisotope to lose, the same amount of isotopes. Okay, so when we plot a half-life, we will see an exponential decay. You can see with this chart here, for each half-life being that, let's assume 1 second, we have a half reduction in terms of the quantity of particles or radioisotopes remaining. You can see here, you should see one afterwards. Okay, so that's what we mean by half-life. It's not a measurement of exact, of a specific quantity. It's a measurement of how long it takes for a chemical or for an isotope to lose half of its radioactive isotopes. It's shown down here. We can actually express this as an equation, like so. So we can find that in general terms, the sample of particles that remain after a given time is given by the following formula. This one here, where E is your exponential, lambda is a decay constant given in seconds to the power 1. If we want to measure the decay constant, it's given by this formula here. So log 2 divided by the time or the half-life of the radioactive isotope. So there's that. Okay, so let's do a couple of calculations using the formula that was given to us. Firstly, the activity of a radioactive source is initially 600 counts per minute, okay, but it drops to 100 after 6 hours. So this is the number of radioisotopes we have after 6 hours. we reach 100. Determine the half-life and the decay constant for this source. Alright, so what we want to do is just write out our equation. So the equation we're dealing with here is this one. Okay, so we know that in terms of time, it's 6 hours. We know that NT is 100, and then we know that N0 is 600. Okay, so let's firstly rearrange the equation. We've got NT as 100, N0 as 600, E minus lambda, and then the time we have here is 6 hours. Okay, or we can write 6 lambda. So what we want to work out is what lambda is. We need to rearrange this equation. Okay, so firstly we're going to rearrange and move the 600 across the equation. So it's 100 over 600 equals to E negative 6 lambda. The next thing we want to do is to get rid of this exponential component. So to get rid of that, we need to log both sides. So if I log both sides, and in your calculator, that'll be the ln. So ln 100 over 600 equals negative 6 lambda. And then to finish ourselves off, lambda would be the log of 100 over 600 divided by negative 6. And that will give us an answer. And that will be negative 0.299 per second. Okay, so that's our wave constant there. The next we need to work out is the half-life of this particular radioactive source. Running out of room here, so let's do this up here. So I know that the wave constant is given by log 2 divided by the half-life. So if I want to find half-life, let's just rearrange everything over. So log 2 divided by negative 0.22 or 0.299. As time is a scalar, we won't need to use any negatives. So the half-life is approximately 2.32 hours. That's the half-life of this particular radioactive source. Okay, next question. Again, it wants us to find the decay constant. Where time has gone is 300. The number of unstable nuclei is 10% of the original. Okay, and then so it's asking us to find the decay. So we could say in our equation, time t, t0, e minus lambda t. So we can say this is 0.1 to represent 10%. The original is equal to 1. The exponential times this value times 300. Okay, so do the exact rearrangement as we did in the question above. So we have the log of 0.1 over 1 divided by negative 300. Okay, so the value for the decay constant will be, well, before I go on, this 300 here, that needs to be converted into seconds, because if you recall, the units for lambda is second inverse. So we know that in 300 years there's 360 days. in 360 days, 24 hours, there's 60 minutes, 60 seconds. Okay, so it ends up being quite a ridiculously long pattern, but the answer we get is approximately 2.43 10 to the power of minus 10 seconds or per second interval. Okay, so there's that given to you here. Alright, the next one we have, it says calculate the nuclear decay constant for lambda for a radioactive sample that has a half-life of 6 hours. So this one is a little bit more straightforward. Substitute into our equation, so it's 2. What we might want to do is, you can leave it in hours, but just remember if it's in hours it's per hour. If we want to leave it in seconds, then obviously we need to times this by 60 minutes times by 60 seconds. So in this case we will get, let's quickly check, a wave constant of 0.000 value there. Next question we have is, what percentage of the nuclei will be left undecayed after 40 days in a radioactive isotope sample with a half-life of 8 days. We can use this equation here. We know that the number of half-lives that's passed, or at least what we're trying to find, the number of half-lives passed, can be found by the total days and the average life or half-life sample of this particular radioisotope. So that is roughly about 5 half-lives that have passed. So that's going to be 5 here. We can say that the original quantity we had was 1 to represent 100%. So NT, in this case NT5, is equal to 1 times 1/2 power to 5. So the final answer we get, let's have a look, is about 0.03125. If we're using 1 as a percentage, okay, so if we're using 1 as a percentage, we are only down to our remaining 3.13 or so % of the radioactive sample. Okay, so that shows you how to do the calculations for nuclear half-life there. Alright, so that concludes this section of the presentation about nuclear half-life. What you need to gauge, or what you need to have learned out of this, is that a nuclear half-life of a radioisotope is the time taken for the original isotope to have lost half of the amount of radioactive isotopes. So the time taken for half of the radioactive nuclei to disappear. We also talked about using models, mathematical models, to predict how many will have decayed at a specific time period. Okay, and we know that lambda is given as s to the power of -1. That is our decay constant. So hopefully you found this part of the video useful. If you have any issues, please feel free to rewatch and recap on whatever I've spoken about. if you're ready to go on to the next lesson, or same lesson, we are going to start talking about nuclear fusion. So see you in that next video.